All right, so let's talk about you being the creative mathematician to make a 3 by 3 matrix that non-zero. That means not everything has to be zero. Not that there can be no zeros, but not every one of them zeros. And the vector b in R3, so what that means is b, put a hat on my vector, has to be a 3 by 1 column vector. Okay, so I'm making a 3 by 3 matrix A so that I cannot get to this vector B from the columns of A. So again, this would be like your A1, A2, and A3. So what would the A's have to look like, and what would B have to look like so that I could not get to the vector B from the matrix A? So I'm going to make up a B. I'm going to say this is 1, 2, and 3. All right, so now I'm going to make up my column vectors so that I cannot get to this vector. So I'm going to say this is 1, 0, 0, 0, 1, 0. And I'm going to say, let's say I cannot get to that last entry. So what if I made 2, 1, 0? So these three column vectors A, I cannot get to this vector B. All right, so this definition of span is really important. So I need to make sure you understand what the word span means. So if I have these vectors, v1 through vp, and they're all in Rn, say, so there's p of them in Rn, then all linear combinations of these is called span of those vectors. So we put these little parentheses in. So span of those vectors is a collection of every single vector that can be written with the c's in front of each of the vectors. So these mean the same thing, and so does this. This means the same thing. It's just a different way of saying it. So vector b is in the span of this. If I can write b as a number times x1 plus a number times x2, and you could write these as c's or x's. So if they're not bold, that means they're constants, right? So in this case, the c's are constants. In this case, the x's are constants. In all of the cases, the v's are vectors. All right. So here we have a matrix A, and I'm given what the vectors are because the columns of the matrix A are the vectors A1, A2, A3. And so now we're going to let W equal the span of all of these vectors. So the question is this vector B in the span of W? So what that is asking, is there a linear combination of these? It can be written as a linear combination of these vectors, right? Is there an x1 that I can find times a1, an x2 times a2, x3 times a3 to get to the vector b? So again, that is making, this is a system that I can put into an augmented matrix. So let's go do it. So 1, 0, negative 4, 3, 0, 3, negative 2, negative 7, negative 2, 6, 3, negative 3. All right, so that's my matrix. So again, I have a 1 in this pivot position here. So first off, I want to get a 0 in that position. So I'm going to say 2 times row 1 and add it to row 3. So carrying this guy along. And I'm not going to do anything to the second row either. So multiplying and adding, I get to here. Okay. So I'm good up to here. So got the zeros underneath my pivot positions. So instead of getting a 1 here, I'm just going to use this 3 as it is. So I'm going to say, let's take, and I'm going to write it over here, let's take negative 2 times row 2 and then add it to row 3. All right, so then let's do that. I'm going to keep the first row the same. I'm going to keep the second row the same. And the third row, I get this. Okay, Now let's stop and look at what the question is. Is this B in W? So this is in the span of, which means is it a linear combination? By looking at this augmented matrix that I have here, I can say yes, B is in W since this is consistent. So this augmented matrix is consistent, means that the vector B is a linear combination of the A's. It's in W. Okay, so what does it mean to count the number of vectors in the span of a set of vectors? So a span of a set of vectors are all the linear combinations of the vectors A. So a vector in W, so if I had wanted to write out what the set of vectors of W could be, I could have 2 times A1, comma, I could have 0 times A2, comma, I could have A1 plus A2, comma, it goes on, think about it, forever. So there are infinitely many vectors in W. How about this question? How many vectors are in the set that has these vectors in it? There are only 3. So this word span is huge. That's the one. That's what's telling us to take linear combination. So explain this difference between this. The span of these vectors is a way of saying the linear, or I should say all the linear combinations of these 3 vectors. This is saying 3 vectors are in the set. So this gives you the linear combinations, all the different ways you could add and subtract combinations of those 3 vectors. All right, show that A1 is in W. So show I can get to A1 by a linear combination of the vectors A1, A2, and A3. Can I do it? I think I can. Let's let C1 be 1 and C2 and C3 be 0.